Hi, this is Han Wen from Huawei North Arc Lab. I will present our work on using noise-enhanced supervised autoencoder to boost the generalization capability in cross-domain few-shot learning. This is the joint work of researchers in Huawei and Chung from University of British Columbia. In this work, we target at cross-domain few-shot learning problem with the goal of recognizing classes in target domain with few labeled samples. We have enough data in source domain to borrow information, but the marginal distributions of data in source and target domains are quite different. For example, the source domain contains data on natural objects from daily life, while target domains contain data on medical images, satellite images, etc. Many works show that prior meta-learning-based few-shot learning methods fail to generalize well and perform poorly under a cross-domain few-shot learning setting. They even underperform the traditional transfer learning methods. Our work is based on the following observations. As you can see from the figure, a competent feature extractor FA fits the source domain very well, yet it fails when transferred to different classes from the target domain. A less perfect feature extractor on the source dataset, FB, however, may have stronger generalization capability and perform well in target domain. We observe the trade-off between the accuracy and the generalization capability of the model trained on the source domain. Therefore, we focus on increasing the generalization capability of the transfer learning-based methods and investigate a multitask learning schema that implements a novel noise-enhanced supervised autoencoder. Specifically, during pre-training stage, we develop an autoencoder that jointly predicts the labels of inputs and reconstructs the inputs. We also consider extracted images as noisy inputs and feed them back to the encoder for classification. During fine-tuning, we develop a two-step procedure to better adapt the model to the target domain. First, we use autoencoder to reconstruct the images for a few epochs by minimizing the reconstruction loss. Second, we only train the encoder by minimizing the classification loss. We conduct extensive experiments on multiple benchmark datasets and various backbone architectures, the COM4 and the ResNet10. We self-designed the decoder that is roughly symmetric to the encoder. We also tested 4 combinations of loss functions. During pre-training, we tested cross-interface classification loss with and without batch spectral regularization. During fine-tuning, we tested cross-interface classification loss and distance-based matrix loss. Evaluation is carried under 5-way K-shot, where K could be 5, 20, and 50 by 600 repetitions. We do ablation study to show that, first, under the same loss setting, our proposed method boosts the generalization capability and obtains consistently better performance on the target domain than the traditional transfer learning-based methods. The noise enhancement that predicts class labels of reconstructed images is necessary in our method and can greatly improve the generalization capability during pre-training. Third, the proposed two-step fine-tuning procedure achieves better domain adaptation and leads to better performance than the traditional one-step fine-tuning. Moreover, we also quantitatively measure the discriminability of the feature embeddings by the intra-class correlation, the ICC. The ICC is defined as the ratio of inter-class variation over the intra-class variation. Therefore, the larger the ICC, the features in different classes are more separated, or the features within the same classes are more concentrated. The results should suggest that encoder pre-trained with our method is not as discriminative as training with traditional classification laws of source domain, but it generalizes well and performs better on the target domain. Our method achieves the state-of-the-art results across all the benchmark datasets under different evaluation settings. And that's all for our presentation. Thank you.